Thanks a lot for coming. Today, my name's Jim Roskind, and I'm going to be speaking with Mahmoud Ragab about delivering great experiences with QUIC on Amazon CloudFront. If you came looking for a technical background, like how did this QUIC stuff come to be? What were the trade-offs? Why did they decide what to do? This is a great place to be. If you didn't, this is a good time to leave. There'll be some geek stuff, and I'm going to talk really fast because I have a lot of content. So be ready. First, the question. There we go. Why is Jim Roskind talking about QUIC? The answer is I actually architected, designed, and led the development of QUIC. QUIC stands for Quick UDP Internet Connections, and it evolved into IETF's HTTP 3 standard, which came out fairly recently. If you wonder where I got the background to do some of this stuff, in '95 I was working at Netscape on browser and server security. I helped design SSL 2.0, which was TLS 1.0, designed signed Java, was Netscape's Java security architect. My joke is I used to fix bugs that were reported to the New York Times and the Wall Street Journal, but that's a different story. In 2008, I worked for Google, making Chrome go faster. I proposed, architected, designed metrics infrastructure for Chrome, which is really a central point in the design of this entire protocol. This protocol is different from many others because it was developed out there on the internet, understanding what the internet does to packets. And I also implemented DNS pre-resolution and TCP pre-connection. 2016, I joined Amazon as a VP/distinguished engineer. So QUIC, I told you it stands for Quick UDP Internet Connections. The idea is it's a protocol intending to supplant HTTP, it's going to be a tongue twister from you the whole time, and more. It provides cryptographic privacy and tamper resistance, historically comparable to TLS, but now evolved to actually use full-blown TLS. We multiplex requests, much like SPDY or HTTP2 does, to put everything down a single line, which helps with congestion control, and also improves latency and reduces the variance between the multiple requests. Again, I'll talk more about this during the talk. And finally, it sequenced UDP packets. So we changed the idea of UDP being a user datagram protocol to being a sequence of UDP packets. But why do we need or want to use it? Well, QUIC is all about speed. It's all about user latency. We want faster and more reliable connections and fewer round trips. Round trips are going to be a big point we'll talk about on the next slide. We want to reduce latency and variance in delivery of bytes. And we wanted better web performance in congested networks, which was one of the questions someone before this talk started to ask me about. And Amazon CloudFront supports HTTP 3. It's available worldwide with full TLS security, and you should enable it. The overview of the talk, I'm going to talk about the context and justification for creating this, including the background and history of HTTP and latency and bandwidth, talk about the problems of the different versions of HTTP, as well as solutions, and then we'll talk about a Snapchat deployment using Amazon CloudFront. Finally, we'll get to Q&A, assuming I talk really fast, which unfortunately you may see. Context for developing a new protocol, the first thing you have to be is very customer obsessed, measurement focused. By the way, that's a leadership principle at Amazon is focus on the customer, obsess over the customer. Don't keep the customer waiting, reduce the latency. And then to design a protocol, you really have to stand on the shoulders of giants. Use the expertise, this is the protocol giants, expertise for support of TLS. TLS was really hard to design and debug and develop. You have to use as much as you can of this brilliant work. Recent deployments of SPDY, HTTP2, involve multiplexing. Again, tremendous forward progress. Use those ideas. Finally, use customer metrics on the infrastructure to be sure you're going in the right direction, constantly checking. And lastly, heavily depend on luck, because if skill ever lets you down, luck is your answer. Okay, so we get to details of pre-existing problems. Well, it all starts with the elephant in the room, RTT, round trip time. And it can be up around 400 milliseconds from some points of presence to actual clients. And that's almost half a second. Now, it's not just the speed of light. Speed of light is something, but the US cross-country is only about 20 milliseconds. But the truth is a packet going between routers traversing the country actually takes closer to 60 to 100 milliseconds. So you have to realize there's significant latency even here in the United States, let alone in, as I say, I think it's India and the Ukraine and maybe Russia where I used to see extremely large latencies. If you want to target delivering your content to people in under 200 milliseconds, you have to go for the best standards, and that means you can't afford many of these round trips. And round trips come in very surprising, interesting places. The first thing to realize is historically, HTTP 1.0, the request uses a fresh TCP connection every single time. That means that these HTTP requests are very expensive. And an example, I can't give the exact name of the site, The names have been changed to protect the innocent. This site used 150 HTTP requests on their homepage. It was not uncommon, all right? That's kind of a problem. So let's look at why connections are a little bit, or you gotta change the microphone or you gotta throw me off the stage.
You're one slide ahead, so you want to move the slide.
Wow. I should look at that one instead of this one. Very tricky. Have you all been reading the slide before or after? Oh, crap. I was just testing to see if anyone was listening to me. It's good that you were listening. I'll look at the other screen now. It's good I have plants in the audience to set me straight. All right, so RTT up to 4, speed of light. Gosh, that's what I just said. Yeah, there's a pattern. Crap. Okay, TCP connection establishment. What does it involve? It starts with a client, typically a browser saying SYN. That's, hey, can we talk? And the answer comes back, SYN-ACK. Yeah, I'm willing to talk to you. All right, and then we send an ACK, and now we're ready to go. We've just wasted one round trip, unfortunately. That's potentially, if we were in India, 400 milliseconds. 50 milliseconds median in the United States. That's a little bit unfortunate. Then you'd say, well, why did you wait? Why didn't you just say, hey, I want to talk, and start talking? Well, the answer is this thing called a SYN flood attack. SYN flood attacks historically are, I'm a bad guy. I say, SYN. In fact, I say, SYN, 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 SYN. And the server on the other side goes, SYN, oh my gosh, you want to talk? I better reserve memory, get ready. And I send out an answer. I've just reserved memory. Another one, wow, he really is talkative. Reserve memory, send another one. Soon I explode, I ran out of memory. That's called a SYN flood attack. That was bad. Instead, they changed it. They said, listen, I am not going to answer the phone until you respond to this darn SYN-ACK, and I know you're there. See, they're not stupid. And so they move forward. So that was blocking SYN flood attacks. So are we out of that? Not quite. Because then I go, I know what I'm going to do. Suddenly I'm an attacker here. SYN, 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 SYN. By the way, my return address is Mahmoud's. It's called a blowback attack. I can convince a server to start hammering this other site, even though I'm just sending little itty-bitty packets called SYNs. That's not very good. And now you already realize I'm just at TCP. I haven't even gotten to TLS yet. And already you realize servers can't be very trusting. Security is already lurking at the TCP level. And then we go to TLS. Remember, that was a round trip just to get permission to talk. And finally, the client says, now that I can talk, could we talk SSL, please? And the server says, sure, we can talk SSL. Here is my public key certificate. That's called a server hello. And I go, wow, what a surprise, the same one as you gave me yesterday. Okay, we'll ignore that fact. Okay, here's a key exchange. I propose a key. And here's the key. And the server says, let me add some entropy, because I like to be really secure. Sends it back to me. So we're probably wasting 2 round trips here. Remember, we spent 1 round trip in TCP, 2 round trips here in SSL land. I'd get away with 1. But we'll call it 3 total. And if we're in India, that's 3 times 400 milliseconds. Quick, who does the multiplication? 1.2, you got it right. Okay, 1.2 seconds, that's a lot. That's a lot to wait. So then someone said, gee, what can we do about this? I know, we'll pipeline. We'll reuse the connection. This is called HTTP 1.1. I'm sorry if you already know all about this, but I think it's actually a pretty interesting and helps you fill up the background of why we got here and how we got here. We tried to reuse the connection. That's a natural thing. Unfortunately, there are 2 problems. The first is in-order response. Suppose I said, send me a GIF. Also, by the way, look up the search result and send me another GIF. Well, you'd sort of go, GIF? Sure, I'll start pushing that out. And then the search result, 1 minute while I do this. Unfortunately, the channel goes idle. And I can't send the other GIF till I get the result of the search, because the rule in HTTP 1.1 is in-order replies. I make requests, they must come back in order. Okay, that's a little bit bad. We have some head-of-line blocking due to in-order response, but there's something even worse. And that is, some people thought of this differently. Some people thought the way it would work is, I'd send a request, he would send me my response, and then I could clear the buffer, and now I'd send another one. Other people realized it would be really cool to say, request, 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 and get 3 responses back eventually. So some of those servers deleted the input buffer. Gulp. Okay? Some of them didn't. The way you could find out is if your site stopped working, then you knew you were in trouble, and what most people decided is to not use HTTP 1.1. The one time you could use it was when you're in a data center and you controlled both ends. In general, it was too dangerous to use effectively. The in-order replies also are a problem. As I say, even if you tried to use it, you didn't really like the fact that it got hung up on a slow response. Well, now that HTTP 1.1 didn't really solve all the problems of the world, people tried to start working around it. The first and obvious thing is, why don't I just open several parallel connections? Why do I wait for this thing to be usable? So I'll open a lot. But unfortunately, I think I mentioned before that one site requested 150 resources. Now, a lot of servers aren't really ready for 150 simultaneous requests from one user. See, that was behind the back one. Okay, they weren't ready for requests from one user. And so they did little negotiations back and forth, and soon browsers agreed, listen, we won't send more than 6 at a time. Okay, that calmed people down, but still we have 6. That's still quite a few. And then the servers that really were big places, they said, if I really want to do it, and I was willing to pay the money and buy the bandwidth and buy the servers, I'll have www.example.com, I'll have images.example.com, I'll have news.example.com, video.example, I'll have a multitude of domains. And in fact, that's what this interesting site did with 150 resources. They actually got 17 distinct domains to serve things. Whew, that was a lot. By the way, if you do the fast multiplication of 6 times 17, do you know what that is? 102. So 102 isn't the full 150. So they still had some things that were reusing the connections, but still they got a lot of parallel bandwidth. Unfortunately, all those connections were sharing the same physical connection and causing congestion. They're all fighting with each other, and you never know which one is going to lose a packet and which one is going to slow down. And if you're unlucky, it's going to be the JavaScript that you dearly needed. This was undesirable. But that's not all. It turns out when you start these connections, the truth is, historically, the good old days, you got to send 2 packets. If you got an ACK back from that, you would send 4 packets. If you got ACKs back from those, you would go to 8. This is called slow start. Why they called exponential growth slow start is a different issue. But that's what they called it. This is slow start at the start of a TCP connection. And unfortunately, that meant that if I need to send, say, 20 packets in a connection, which is actually a common sort of thing to do, I had to spend 3 or 4 round trips. TCP tried to help us by bumping it from, say, 12 to 16, but still, I had these parallel connections all fighting for bandwidth. And worse than that, the first connection says, hi, I'm Chromium, and by the way, these are my cookies. The second one says, hi, I'm Chromium, and these are my cookies. Anyone see a similarity? Yeah, they're all saying the same thing multitude times, 100 times in parallel. What a waste of bandwidth. So this is a problem. Kudos to Mike Belshi and Roberto Pian for driving forward to SPDY. SPDY is the basis of HTTP2. Each get and put is put into this multiplex stream, and the idea is that now I don't have to worry about in-order response. Remember that example I said, get me a GIF, get me a search result, get me a GIF? It could start returning the GIF, then it would send off with their search result, start returning the second GIF. Oh, I have the search result? Let's stop sending the GIF. Let's inject some search results. They're multiplexed. We can put them in and tease them out automatically. We can get out-of-order responses. We can prioritize JavaScript and style sheets. HTTP2, very cool, very clever. And SPDY HTTP2 also reduces the redundancy. They did data compression of those headers. It no longer had to say each time, I am a Chromium browser, and I have these cookies. It says that once, and it keeps referencing it. That's data compression. That's adding efficiencies. Wow, this is really helping the world. And the streams shared a single flow, a single congestion window. So now the whole stream would slow down or go forward, and we'd at least get to prioritize the things that we wanted to put on the stream as soon as possible. No fighting and variance among the streams. But there are weaknesses. See, it's never as pretty as you hope. Okay, the weakness here is TCP's initial congestion window, I said, was 2 packets. That was actually terrible. Contrast that with the 6 parallel connections. 6 parallel connections could easily send 12 packets. While poor little SPDY is sending 2. Next thing, SPDY sends 4. This sends 24. You suddenly realize the parallel connections are ramping up much faster. This is unfair. This is causing people to not want SPDY, which is a great thing. And then, that's a strange thing. Why should we be so nice? This old-fashioned method, which is wasting the bandwidth of the universe. Then, when we get beyond that into the steady state of TCP, who knows what the steady state of TCP? Yeah, there's a little bit of sawtooth wave. Who's seen the sawtooth? Well, some people have. The interesting thing is we have what's called AIMD, additive increase, multiplicative decrease. When we lose a packet, we often reduce the bandwidth. Historically, it was by a factor of 2 to half the size. These days, I think we cut it down by about 30%. Let's think about what happens now. I have 6 connections in parallel, and I lose 1 packet. Obviously, only one of the streams is impacted, and so I end up losing 1/2 of 1/6 of the traffic. Total I've lost, 1/12 of my bandwidth. with 6 parallel connections. In SPDY, when I lose one packet, all of a sudden I lose 50% of my bandwidth. Holy cow. These systems aren't being very fair to this tremendous forward advancement. So now I had to go beg, Mr. TCP people, couldn't we change this? Can you be a little bit friendlier about the fact that I have six connections multiplexed? So we were making some progress cleaning these things up, but in order TCP delivery still came to lurk. Turns out TCP, if you look close, it's a stream of bytes which are all in order. And once you lose one packet, under the covers at the kernel level, it holds on to everything, and it will not allow you to see the future packets until it resolves that missing packet. This causes more ahead-of-line blocking. Because SPDY is using TCP, finally, when it resolves that packet via a NAC, please retransmit it. Here it is. That's another round trip. We pause the channel effectively. This was bad. And then if you didn't feel bad about what TCP was doing, turns out if you go one step higher, SSL often encrypts blocks, one block at a time, often using cipher block chaining. Cipher block chaining means we encrypt the block. When we're done with the block, we generate the hash of that, and we use that as part of the initialization vector to decrypt the next block in the series. What does that mean? It means if we lost a packet, we couldn't decrypt the block. If I couldn't decrypt the block, I can't decrypt the next block or the block after. Again, we have head-of-line blocking. So the interesting realization is TCP and TLS are slowing us down. What can we do to go forward? And this is when QUIC really started to come into its own. We want to avoid the head-of-line blocking. TCP and TLS induced head-of-line blocking. We wanted congestion control to be able to evolve even faster. Notice that I couldn't adjust that additive increase in multiplicative rate in TCP very easily. It was part of the kernel settings. So I want to be able to change these things and improve the internet, but we couldn't do it. So we want to stop arguing with our operating system vendors, and a 5 to 10 year deployment rate was just not acceptable. Turns out when you want to change things, it's very slow in general. So was a new protocol feasible? We had to handle packets separately. So the natural thing, if you were in academia, you would decide, well, IP packets, we could define a new IP protocol. Why use UDP? Let's just define a new IP protocol number. But there's a problem with that. I think someone mumbled the problem. The problem is most of your firewalls will block any unknown protocol they haven't seen. So the minor problem is the packets will go nowhere. That was considered a problem, okay? So instead, we said, we'll use UDP. Now, I did get a lot of nasty grams from people saying, don't use UDP. We're going to outlaw it any day now. And I say, well, when you do that, DNS will go away too, so I'll be surprised. But anyway, coming back to reality, the idea was I had to use UDP. That was the only way to make quick forward progress in the design of the protocol. But then you have a lot of questions. Now that I've made the statement, can all my clients actually reach the server using UDP? I heard gamers use it a lot, probably, but maybe the gamers bought extra special equipment or something. I don't know. Network address translation, how does that work with UDP exactly? What about load balancers? They're not used to seeing a stream of UDP packets. Interesting problems. And can servers handle the high loads? So let's take a look at a couple of those problems. The first question is, what about reachability? Can UDP reach our customers? We had to test this around the world. How do we do it? Well, luckily we had this thing called Chrome at the time. And we put inside of it, people opted into assisting us in understanding how to improve efficiency and reliability. So when we were sending data, we also told it to say, do a ping to a server. We set up servers all around the world. We have 1 billion clients all around the world, just very rarely sending a ping here and a ping there. And soon we were able to show that 93.5% of all our clients could, via UDP, reach our Google server. Now, that's not everyone. In fact, actually, the conjecture was that it was corporate firewalls that were blocking it. But so we didn't solve all the world's problems, but 93.5% of the users, we could help them. And then we'd have to fall back to TCP. Okay, that's a pretty reasonable idea. Let's see if we can go forward with that. And then came the general pattern that you'll see throughout this talk. If you build it, they will come. This is my optimistic mantra. We must create, not unfortunately, but realistically, a compelling advantage to use QUIC. And that's what will cause people to come across. It wasn't just solving some of the geek problems that I've talked about, and then I'm going to talk more about. I'll need a compelling advantage. Well, one question, this is another geek problem. How do NATs handle UDP traffic? NATs, network address translation. This is all about the fact that you have dozens of computers in your house. And when they send packets out through your firewall, egressing from your house, the firewall does network address translation. It rewrites those packets assigning a port specifically that it remembers so that when the servers respond to that port, it goes, oh, that goes to your refrigerator's computer. Oh, that goes to your spouse's computer. Each port is assigned. This is called network address translation, the binding. Well, the interesting thing is with TCP, they do this and it works very cleanly. Mwah, very nice. Unfortunately, it knows that when it sees the FIN packet, a FIN is a final packet in a TCP stream. When that finally comes down, it says, no more? Great. I'll erase the binding, and I'll start reassigning the port to someone else. That works great with TCP. UDP, unfortunately, has a timeout because it didn't really expect to see, there is no FIN packet. It has to have a timeout. So I asked the experts, I said, what's the timeout? And they go, oh, we never bothered to standardize that, but the good news is IETF has taken this up, and in 5 to 10 years, we're going to have a 5-minute standard. I go, well, that's nice. And then I knew there's going to be 10 or 15 years after that to deploy it. No, I have to find out what the real answer is, and we had to measure it. And so I told those little browsers to do something cleverer than just ping. Instead of saying ping, I'd say things like, ping, but answer me in 10 seconds. Or I'd say, ping, but answer me in 70 seconds. And each one would randomly choose a number and do its little ping, and then I'd gather the data. And this is what I saw. You'll notice at the bottom, down on the y-axis at the bottom is the probability, 0 at the bottom, of getting no response. So you'll notice the probability of getting no, think of it as down is good. Down is we got a response, okay? And so you'll notice between 0 and 30, see that's a 40 at the bottom, the first, you have 0 is the far left, then comes 40, then comes 80, then comes 120. You'll notice as long as you got just shy of 40, right about 30 seconds, you would do a pretty good job of getting a response. When you were between 30 and 60 seconds, still it wasn't too bad. You might go up to maybe 5 or 10% loss. It looks like 5%. But once you passed 60 seconds, boom, you lost about 40% of the response. So the answer was, it was probably on average, the typical thing was tearing things down after a minute, and certainly a little bit of loss after 30 seconds. What did that mean? It means that if our protocol was going to continue to work in the presence of these teardowns, it had to survive with ports being changed on egress from your home. So that means that since I have timeout complications, I had to tolerate the timeouts and I needed an embedded ID. See, with TCP, they often talk about a 5-tuple. Egress, what is it? Origin IP, origin port, destination IP, destination port, and the fact that it's TCP. Unfortunately, now we're using UDP and we're messing around sometime with that originating port. But yet we intended to make all those packets be considered as a stream. We have to put in a connection ID. Uh-oh. We solve a problem, we make a new one. Now the load balancers can't just look at IPs and ports anymore. They have to look deeper. So then comes the question, can they deal with this? Boy, lots of questions. Now, so the answer, the questions rise and simply say, can the infrastructure for UDP handle all these complications? The first question is, TCP handling is highly evolved. In fact, we typically do TCP offload to hardware and network interface cards because we wanted to go faster and we didn't want to tie up the server. And the kernel hacker said, don't worry, Jim. We could do it, but by the way, we're not going to do very much for you right now because we're too busy and you don't really have a protocol. Okay, that's a problem. And the load balancer folks, they also told me they could do this. But again, guess what? They don't want to do anything for me because they're too busy and I don't have a protocol. But the good news is if I just beat around the load balancer trick, if I don't want to use a load balancer, what do I do? Just hit one IP address and don't do load balancing. So we were able to build prototype versions that worked pretty nicely. And perpetual optimism is a force multiplier. Right? Nice quote from Colin Powell. You have to constantly be optimistic as you go through this road. So can we bring value to customers? I talked about this. Can we securely, we had all those geek things which we seem to be fighting our way past. But again, to sell something, we really need to, that's 35 minutes, that means how long I have left, I think. That's good, I think we're doing good. You might get out of here in time for dinner and certainly before midnight. So can we bring value to the customer? Can we securely start an encrypted stream faster? We think we can. Can we befriend TCP congestion control? Someone asked about congestion control. Can we improve congestion control? Can we actually do better? Can we reduce packet loss? Can we avoid head-of-line blocking? I think we have all of this stuff nailed, but let's take a closer look. Can we start an encrypted stream faster? There's a parallel discussion of TCP fast open, and you send a cryptographic token attesting to the fact that you had source IP ownership. Basically, you got it from the server the last time you were connected. And this was a listen, I spoke to you from this address before, and here's the thing you gave me. You wouldn't have given it to me if it wasn't for real. All right, that's the attestation. And don't let perfect be the enemy of the good. Realize the server could always say no. This was a very different motion from most security protocols historically. Historically, we will go 1, 2, 3, 4. Anything wrong? We blow up, we start again. Instead, I say, can we go 1, 2, 3? And if you're willing to live with it, we'll go 3, 4, 5, 6, 7. And if you're really complaining, then we'll go the slow road. But a lot of the time, we'll go the fast road, the faster road. And now, TLS, for instance, rarely changes server certificates. I mentioned that before. I can speculate that the server certificate I'm about to get is the same one I got yesterday, or certainly 2 hours ago. Even though, and for many servers, that they change it every 6 months or a year. So it's a very high probability hit that they haven't changed it. And we measured this, and we found that about 75% of the time with test servers that we were using, we were able to make forward progress. Again, we're not solving all the world's problems. We're solving a lot of them. Now comes TCP congestion. You know, rule 1 is you're defining a new protocol, don't break the internet. People will get kind of angry if you do that, okay? And actually, by the way, I remember hearing stories about people going to VCs, venture capitalists with, I've got this new video codec. Look at how great it works. Look at how this other one does terribly. And I go, that's because you don't back off, okay? That works great for one connection. You use a couple of them and you'll take down the whole internet. It's a good sell for a VC. You should keep it in mind, but they'll catch on eventually. All right, and so initial congestion control, we'll use TCP style. We'll just adjust the parameters. Being fair, if I'm sending 6 connections down a single pipe, I should get the same benefits as I would get by going with separate connections. When it comes to startup windows, I should get the same connections as doing 6 in parallel. I'm just trying to be, and if I'm only using 2, I should be honest and only get that as an advantage. So we got to change the parameters that you heard in TCP, but be very TCP friendly. And come an interesting thought, though I did notice those TCP guys, they like to burst packets. When they got permission to open up a window, they would just send them as fast as they could. And the interesting realization is packet loss. Packet loss is not because the wire is loose. Packet loss is not because of photons or muons or any of that stuff. Packet loss occurs because a lot of people go into a router for multiple inputs, and they all have to egress out of one output. Unfortunately, sometimes that means you have more gazintas than gazoutas. And when that happens, a queue builds up, unsurprising, and as you'll find out in life, most of these routers have finite memory. So eventually you run out of space, the buffer is full, you drop packets, which really isn't the end of the world. The internet is an equal opportunity destroyer of packets, okay? It destroys the packet, and then the people sending things go, oh, there must be congestion. Additive increase, multiplicative decrease, they cut down their bandwidth, and they rescue this congested link. And so this is the natural affair of the internet. So, but they bursted traffic. Think about that. The problems that we have with congestion involves too many people arriving at once. If it is indeed a bloated buffer, why am I rushing to send all the packets into it when I know that they're all going to sit there waiting? So the interesting question is, could I do pacing? Would pacing really help? And again, how do I know? The answer is I measure. And so this is an example of a very interesting experiment sending 1,200 byte UDP packets. Specifically, I sent 21 packets to warm up the channel because I want to do an A/B test, which reminds me of what Mahmoud will talk about. You have to be very careful when doing A/B tests. You want to get into a very standard situation and now try 2 equal things. So the first thing on the bottom, that yellow line, that shows what happens when I send the 22 packets as fast as I can. Packet 1, packet 2, packet 3, packet 4. All right? There are a total of 24, and as you come down, that shows the probability of packet loss increasing. Up at the top, 100% means no loss. You'll notice that the first knee in the curve happens around 12. It's just to the left of the 13 line. And then a big drop comes around 16. By the time we pass 16 packets of sending them blast, 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 we're down at about 88%, or what does it look like? 87%, 13% packet loss. So if you send them really fast, you lose them. But let's try, now that I did the warm-up with yellow, let's try that experiment again, except there are 2 different ways we do it. One is pacing, paying attention to how fast I got the ACKs back. I realized that when they had to work their way through a knothole, they got slowed down. So even though I said packet, 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 they could only egress packet 1, packet 2, packet 3. Why was I blasting all of them into this queue at once? So the top line says, suppose we pace them out based on the response that we got. And you notice what happens. We have significant reduction in packet loss. And you'll notice, and actually not too surprising, the other line in between the two, which is the blasted, packet 1, packet 2, as fast as you can, drops off rather similar to the warm-up. There is one strange thing you might have noticed. Did anyone notice the strange thing? The strange thing is, what the heck happened to packet 2? Why was packet 2 more likely to die than packet 1 or packet 3? It's an interesting question. I had a conjecture. My conjecture was the router was so busy setting up the route that it didn't have time to answer the phone. And it said, it's just a UDP packet, let it go. It's not that important. That was my theory. So I said, if that theory was true, how could I test the theory? The answer is, gee, if that theory was true, if I sent smaller packets, then the packet 2 would arrive sooner. So I sent 3 separate experiments, and one sent 1,200 bytes, which is just what I did. Another sent 500 byte packets. All 21, by the way, are the same size. Another one sent 100 byte packets. And you'll notice what happened. The 100 byte packet suffered tremendous loss on that second packet. What does this show you? It shows you, well, the second packet hit the router even sooner. And the router was busy. And that's why it had a greater loss probability. So this gives a hint that pacing can really help us. And this is something that TCP was not doing, and something that we can do as we're writing QUIC. So this is saying QUIC can help reduce congestion and reduce packet loss without doing anything special beyond that. Now there are some loose ends. 28 minutes, Yeah, I think I'm doing good. Again, you'll be home by midnight, I guarantee. That was a joke. You don't have to laugh, though. It's not necessary. The QUIC from 50,000 feet, adopt, migrate, and use. How browsers discover QUIC support is an interesting question. How do clients retest QUIC viability? Remember, there's a bunch of mobile users. They're in different places. Sometimes they're at work. Sometimes they're at home. Sometimes they're out, using cellular. Are we sure that we're going faster than TCP and TLS connection using speculation? We want to be sure we limited the blast radius. We want to dot our I's, cross our T's for a lost packet. We get to integrate encryption with packet sequence number. This is sort of cool because we're going to reuse, since we're numbering those UDP packets, because we didn't have to do that with TCP. Now we have to number our packets. We're going to use that as part of the initialization vector to deal and improve the encryption. We're tying together all these loose knots. Let's take a look at some of these pieces. Browser discovery of QUIC. Earlier, HTTPS over TCP says, by the way, if you ever call me back, please feel free to use QUIC. That's the subtle hint that's given, all right? And then when a browser sees that hint under old-fashioned TCP, it says, possibility server supports it. It remembers the server's public key. It remembers this IP address used token, and it gets prepared to try to do a QUIC connection the next time. So future connections go faster than the first one. The browser locally optimizes, and it doesn't have to contact a third party. This is all privacy preserving, locally calculated, and done. It's very, very sweet. Can QUIC reach the server every day? The browser has to race a QUIC hello against the TCP TLS connect each time. And the idea is you send them both roughly at the same time. Notice, remember, TCP is so slow because all it does is a SYN-ACK. By the time we get the SYN-ACK, we'll probably have the QUIC connection fully established. Okay? So we're willing to abandon the TCP connection. And all we really wasted is one packet sent across the net. And we know the servers were set up to abandon the TCP connection because they don't like SYN flood attacks anyway, so it really isn't a problem. And if the QUIC connection works, TCP is abandoned. What happens after QUIC hello? Packets are streamed both directions. ACKs piggyback. They bundle inside with real data, and the congestion control algorithms will evolve. And we have the ability to control this at the actual application layer and not rely on the operating system to evolve. Some other interesting things. Head-of-line blocking is no more. Streams generally honor the UDP packet boundaries, meaning usually when we have a given packet, we say, let's put all the stuff for one stream. Another packet, I can decide what stream I want to put it in. So usually when I lose a packet, it simply damages one stream. The other streams can continue to be parsed because they're decrypted separately. We have to straighten that one stream out, and again, we get to choose at the server side how to send things in the priority order that we want. They're individually encrypted and numbered. By the way, what I just said about multiplexing with HTTP2 is impossible in TCP, but explicit with QUIC. And the point is TCP has that head-of-line blocking. When it loses something, it can't see the other packets that come after it. They're individually encrypted. We avoid cipher block chaining meticulously, and each packet is decrypted separately. Head-of-line blocking has minimal impact, and I'm sure you've read, if you follow this on the internet, there'll be interesting publications, and YouTube mentions they have tremendous improvement in the rebuffer rate. Okay. This is all goodness. How are packets acknowledged? Well, the ACKs are in the control stream, but they're now embedded inside an encrypted packet. All packets are encrypted. A malicious third party can't inject a TCP-style FIN. There are certain unnamed countries which at the border to the country, sometimes they decide they want to tear down a connection. You know what it takes to tear down a connection? You just send a FIN to both ends, and each one thinks the other end sent the FIN. I don't know why they said to tear it down, but they said to tear it down. It's over. So one packet in each direction, you can tear down a connection. In fact, so that's sort of interesting. You can't do that with QUIC because it's inside the encrypted, authenticated message. So that doesn't work. In fact, you can't even see what ACKs are going by. You can't even see whether you're damaging or slowing them down very much. In fact, we can go even one step further, that when the selective ACK can hitchhike with the real data. There's something really cool that I was trying to say about here. Optimistic ACK attack. It turns out the other cool thing that you can do, you could kill a packet, and then you could send a message to the sender saying, oh yes, I received that. Don't bother to retransmit it. Think of what havoc this would wreak upon a TCP connection. The receiver is waiting, and the server was told, no, don't bother to send it, I got it. Basically, you collapse, you break a TCP connection. You can do this with TCP underneath SSL. You could send the FIN, you can mess with the ACKs. There's also an optimistic ACK attack that gets even meaner. I think you can look it up on the internet. It's really bizarre what you can do with these things because the ACKs are exposed. How are packet losses handled? Well, QUIC rebundles lost data in a new packet, a brand new packet, a new number. QUIC never retransmits lost packets. It retransmits the data in a new place. And TCP, in contrast, retransmits the lost packet. That means that when you receive a packet in TCP, you're wondering, did it just get delayed somewhere in a long queue? Even though I said I didn't get it and I asked for a retransmission. Was it a retransmission? Or was it a delay? I'm not sure. There is never that question in QUIC. If you get a packet, it was the original packet as sent. So these are advantages. This allows you to understand much better. It enhances the ability, again, to develop congestion algorithms with better knowledge. And we have constantly advancing packet sequence numbers help. The congestion window limits the number of outstanding packets. There's a lot of things that start falling in place here. The result is IETF QUIC emerged as HTTP 3. Google QUIC supports 90% of all Chrome traffic. This has been reported in the press. Years of testing worldwide, and then AWS, Google, and others implemented the IETF QUIC standards. And we have faster connection, reduced latency variance, and customers around the world benefit. See, sometimes I slow down. I like to slow down for those good things. Summary of QUIC. Maybe I've said it too many times. What is it? It's the next generation HTTP protocol and more. It replaces TCP plus TLS plus HTTP2 using UDP. Provides guaranteed delivery, faster cryptographic connection establishment, multiplexes a stream just like HTTP2 with one congestion-controlled flow, improved latency and reduced variance, and it allows us to evolve and continue to evolve our congestion control algorithms. And Amazon CloudFront supports IETF QUIC, as do browsers. If that wasn't enough, there's a forward-looking company called Snap who sent Mahmoud to talk about how they've tried to implement this and analyze their results. So, Mahmoud? There you are.
Thank you. Hello, everyone. My name is Mahmoud Ragab. I'm an engineering manager at Snapchat. And today I'm going to talk about how Snap and AWS has worked together to test and release the usage of QUIC for our users. This one. So the way I'm going to talk about this, the first part, I will give you a quick introduction to Snap content delivery system and how we deliver content to our users. And then I'll talk a little bit about Snap's interest in QUIC. And then, which I think is the most important part of my presentation, is how we tested QUIC at scale and how we made sure that QUIC is working for our users and for our use cases. I'll mention some of the challenges that we have made and how we overcame them. And then I'll talk about the results. This might be the most exciting part. And then at the end, I'll give you some of the lessons learned and the next steps. So Snapchat aspires to be the fastest way to communicate. This is part of our mission. We want users to be able to communicate with each other as fast as possible. And for my infrastructure team, we quickly realized that the fastest way to do this and the best way to do this is to stay on top of all the cutting-edge technology and continue to experiment with new technologies as they come out and make sure we're using them. Snap also has a long-term investment with QUIC. We've been using QUIC in different workloads in the past, and we've always realized the impact and how powerful QUIC is when it comes to network performance, which is important to us. On the other side, Snap is using Amazon CloudFront as one of its core infrastructure components to deliver media, as I'm going to talk about. So when the CloudFront team came to us and they said that they're interested to work with us to test and implement QUIC or HTTP3, we were very, very excited to jump on this opportunity and work with them. And what's better than Snapchat's 330 million daily active users all around the world to test the performance of QUIC? But we also understand that new technologies needs validation. Just because it's new and shiny doesn't mean it will work for us. So we wanted to be thorough, and we wanted to make sure that we're testing it and experimenting with it and making sure we're seeing the results that we want to see. So how did we do it? This is a quick, maybe a very oversimplified version of how Snapchat delivers media to the users. At a very simple view, we have a Snapchat user, and then we have a CloudFront distribution or a CloudFront POP that is overlooking an Amazon S3 bucket. We put the media in the S3 bucket, and then the users send an HTTP GET request to the CloudFront distribution. The CloudFront distribution, it either has the content cached. In this case, it will return the results. And if it's not cached, it will send the request back to the S3 bucket, fetch the content, cache it, and then return it to the user. And if you look carefully here, there is two links, right? There is the link between the user and the CloudFront distribution, and then there is the link between the CloudFront distribution and the Amazon S3 bucket. The first one is usually on the public internet. There is internet providers in between. This is where it's slow, there is high latency, and there is usually high error rate. There's packet loss. The other link between the CloudFront and the S3 bucket, this is usually on the AWS backbone, fiber optics, very fast, very low error rate. So this is the first link is usually what we are interested in trying to optimize, the connection between the user and the CloudFront distribution. So how do we measure it? How do we know how it works? Turns out our Snapchat clients as well sends what we call a network event log with every network request. They collect these logs on the client, and then they send it to a server, an Amazon EC2 server. This log says, hey, I made this request to this domain, and it has a bunch of information as well. Things like time to first byte, time to last byte, connection time, response code, location, POP, client origin, and so on and so forth. We collect all these logs, and we store them. We sample them, we store them in a database, and then we could offline look at them and understand the performance better. So now we have QUIC, and we want to try to test it and see if it works. So how do we do it? Our first idea was to do what we call a production mirroring. So on the top here, we have our production distribution. It does not have QUIC. This is what our 90% of the users are using to download media. And then we spin off a different distribution. Let's call it a test distribution. This one has a different domain. This one has QUIC enabled. It should be identical to the production. The only difference is it has QUIC enabled. And then we reroute some of our users, let's just say 10% of them, to use the test domain and the test distribution that has QUIC enabled. At the face of it, this sounds like a great idea to test it. But every time we do this and we look at the results, we find out that the production is doing better. And we try to look deeper into this and try to understand why this is the problem. And it turns out it's not because QUIC is bad. It's because we're giving the production distribution an unfair advantage by having a lot of users using it. Things like this domain becomes more popular because there's more users using it, so the DNS lookup is faster. Cache hit rate on the CloudFront distribution is much higher because there is a lot of users are trying to download the media versus a much smaller number of users trying to download from our test domain. So again, every time we run this experiment, we look at it and it seems like QUIC is not performing as good as the production, but it turned out that our experiment setup is actually wrong. What's a better way to do this? Is to actually have two separate distributions and what we call it a counterfactual. In this case, we have the production distribution. We do not touch it. It's not part of our experiment. We don't even look at the performance. And then we have two separate counterfactuals. Those are a mirror of the production. They're pointing to the same Amazon S3 bucket. They have the same number of users. They have two different brand new domains. And they have the same number of users downloading media. And the only difference is one of them has QUIC enabled and the other one has QUIC disabled. All of them are sending the network event logs, and then we could look at this offline and decide how good or bad QUIC enablement made to our user performance. But it's not that simple. I think the way I prescribe the problem is actually oversimplified. In fact, CloudFront is not just one distribution that you point at. CloudFront has multiple POPs around the world. And there is regional caching, there's different data centers. It's not only one S3 bucket in one location. There's different S3 buckets in multiple locations. The other problem is there is tons of ASNs. ASNs are like the internet providers between the user and the CloudFront distribution. Some of them would support QUIC, some of them cannot support QUIC, some of them have higher error rate, lower error rate, and so on and so forth. Also, we discovered that the platform you're using matters. If you're using Android and iPhone, those handles QUIC differently. There is tons of client libraries out there, and each one of them has its own implementation of the client side of QUIC and have different configuration, different implementation, and those matters as well. So these are, I think, the results. We are using, to measure the result, we're using what's called the trimmed mean. And if you don't know what trimmed mean is, Jim has actually an excellent talk about it. I think he's going to talk about it on Wednesday. I highly recommend that you guys attend that. But a simplified version is this is the average of all the requests after you exclude the worst 1% of the requests that you had. As you can see, time to first byte with QUIC is probably always the biggest gain we see because there is zero RTT, connection establishment is very fast, and you can reuse connection. So we usually see 6 to 10% improvement in time to first byte. For time to last byte, I think it's going to depend on your object size, if you have bigger objects versus smaller. But for our use cases, we saw an improvement of 6%. Lessons learned. As I said, I think what I really hope everyone takes away from this presentation, new technology is cool, but you have to test it, and you have to test it carefully. You have to make sure that your experiment setup is proper, and you're seeing the results that you're expecting. The other important thing is you need to slice and dice your experiment data very, very carefully. You have to look at different iOSs, whether it's a high-end device or a low-end device, whether it's one ISP or the other. The people have like faster internet, slower internet, and all those things matter. The other interesting thing is using a representative sample is very important. We have so many experiments where we start the experiment, we see results, we either get excited or disappointed, and once we dial up the numbers of the users as part of the experiment more, the results start to change. This is testing something that complex is very hard, and I'm just advise everyone to use this as an iterative process. Just test and try again and see what's wrong, look at your data, and maybe test again. I think that's it. With that, I'll probably hand the mic back to Jim to give more information about Amazon's HTTP QUIC.
Assuming is my microphone on? Yes. I just want to double down on what Mahmoud just brought up. It's really interesting to understand that setting up experiments is not as easy as it sounds. You have to put in a lot of care. And so it was very, very nice. Take a close look at what he does and what he did and what his team did, and understand that if you want to do experiments for anything, but certainly in this domain, be careful to make sure it's an A to B test, just as I did with the 21 packets with a warm-up to get to exactly the same state. You've got to do it. It's a very, very nice work. Be sure, look carefully at that if you didn't catch the subtlety of what he presented. It was really nice. But the big thing then is, if you want to read more about AWS support and CloudFront, we have a link. And if you want to read more about the tales of woe and interesting design elements, read the specification and rationale I wrote. 70-page design spec cut down to a mere 40 pages. Actually, there's a lot of good stuff in there. You'll be surprised. Anyway, search for IETF QUIC and read the latest RFC for standardization if you were curious to look at it that way. And for trim mean, he mentioned there's a talk AMZ 302 this Wednesday. I'll talk about trim mean, as he's noted, and why it's a much better stat for looking at latency than merely things like P50, P90, and others. I don't want to give that whole talk now, even though I talk too fast. So now, I want to say thank you. We'll take some questions, but the most important thing you got to realize is you have to say good stuff about us, okay? so we get paid, okay? Otherwise, they don't pay us. Well, maybe I'm exaggerating a little. Okay, anyway, thank you very much for coming, but do you have questions?